for the intro. Okay, yeah. So well, let's start. What is the async working group? So um, async Rust is in this kind of interesting place in that you can do async programming today, very much so. Like the key kind of async and await keywords are implemented, stable. There's some great libraries, da 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 da. But it's not exactly like a great programming experience. It's extremely rough around the edges. There's a lot of kind of like really key functionality that's missing. And so the async working group was formed to fix that. And it cuts across kind of language and libraries and tooling. So it's a real kind of like cross-team effort. And it's doing a lot of exciting work. And today I'm just going to talk about the Portability and Interoperability initiative, but there are other initiatives looking at things like async functions everywhere. So letting you have async methods and traits or async closures, or initiatives looking at improving debugging async code, and so forth. So it's quite a wide-ranging initiative with a whole bunch of folk working on it. But like I want to kind of like step back a little bit because I want to kind of like make this talk open for people who aren't like really heavily into async programming already. And I also want to, if you are really heavily into async programming already, I want you to kind of like share the mindset that presumably you once had when you discovered async programming in Rust, and what somebody new to that today would feel like. So async programming in Rust, I'm going to go through an example, and the example is reading a file. So I'm going to start, like, let's just ignore all the async stuff. This is what if we were writing regular synchronous Rust, this is what it would look like. So this is, it's just a short function for reading a file. It takes the path of the file as an argument, and it returns the contents of that file or an error. So the first thing we do on the first line, we open the file. Okay, good. Next, we create a string that we're going to read the contents into. And then we call this function read to string, which reads the context of the file into the string buffer. Then, if there was no error, we return that string. Easy peasy. And then calling this function, which we've done the last line in the example, it's so trivial that it's not really even worth me explaining. You just call it. So there's a couple of things that I want to point out. The first is that read to string is not a function on file. It's a function on the read trait, which is an abstraction over any resource you can read from. That's going to be important later, but I just wanted to point that out now. What's actually interesting to our kind of motivation here is that when we're doing this I/O, when we're opening the file, or when we're reading from the file, we're actually asking the operating system to do that. And it's going to take quite a long time to do it. I mean, not like really a long time, like a fraction of a second, but like a long time in computer terms, right? And whilst that's happening, the user process, or at least this thread, is just sat there doing nothing. It's literally just waiting for the operating system to complete. And that's just a waste of time. And so that's often the case with I/O. And so asynchronous Rust is basically trying to answer the question, like, what if we could actually use that time productively rather than just sitting waiting, and do that without having to use kind of like full operating system threads for various reasons that it's not worth getting into right now. Okay, so if we wanted to do it asynchronously, first thing we need to do is you need to use the async keyword to say this is an async function. And one effect that has is that when we call the function, it's not quite as simple as before. Actually, calling the function now won't actually do anything. We have to await the results of that function. And this is basically saying, well, this is a function that potentially could take a long time to execute. So let's give the runtime an opportunity to do something else while we're waiting. This is the whole point that I just talked about async Rust giving you an opportunity to do other things while you're waiting. The other thing that the async keyword lets you do, this is an async function, and that means that within this function, we can await other async functions. So when we had this file open to open the file, and when we had this read to string to read from the file, these two IO functions, now we want to await the results. And again, this is signaling to the runtime. These are asynchronous functions. Here's an opportunity to get some other work done while we're waiting for the operating system to finish off doing what we asked of it. Wait, did that? Sorry. So there's a couple of problems though. So far so good, right? You think you're going to do asynchronous programming, you've just sprinkled around a few more keywords, and hopefully things have got more performant, right? We're going to be able to do stuff while we're waiting, which is great. But there's a couple of problems. First of all, these two functions, like file open in the standard library and read to string on the read trait from the standard library, they're not actually asynchronous functions. So we can't wait for them. And in fact, there are no asynchronous functions like this in the standard library. So somewhere we've got to find like functionality that does what we were doing before, but asynchronously. The second problem with this is actually calling this function at all. So I said we had to await calling this function, but I also said that you can only call await inside an async function. Now you can call inside an async block as well, but that's a detail. The fact is that you have this chicken and egg situation in that if you actually try and call this function from main, the compiler is going to complain at you. It's going to give you the error that's on the slide. And we have to find some way to get out of this kind of chicken and egg thing and actually have a way to call async functions. So that's kind of, these are two kind of big problems, and hopefully you'll see in a few slides' time why that's kind of what to do with the interoperability and portability stuff. But let's try and solve these problems. Let's imagine that we're just starting to do asynchronous Rust. Well, kind of, this is a sucky situation, actually. The compiler error here is correct, but it's not really, doesn't actually help us solve the problem. But let's just imagine that somehow you know that you need a runtime. Like I've said the word runtime a few times, and so maybe you know that you need to kind of somehow you know that you need to go looking for a runtime. Well, let's go to the docs. Great place to start when you're learning is to go to the documentation. Here's kind of the official, or as official as it gets, documentation for async programming. This is the async book on the Rustlang website. Okay, async runtime. So this looks promising. Async runtimes are libraries used for executing async applications. Well, that sounds like what we want to do here, right? And so it continues. Runtimes usually bundle together a reactor with one or more executors. I don't know what those words mean, but let's carry on. Reactors provide subscription mechanisms for external events like Async IO. Well, Async IO is promising. We do want to do some IO, inter-process communication, and timers. In async runtime, subscribers are typically, and it carries on, and frankly, it's just kind of word salad, and it's not really helping me. But let's press on. The future's great. Well, if you've just started writing some like async code, like we've talked about async functions, we've talked about async IO. I haven't actually mentioned futures at all. Now, if you're kind of like deep in the kind of like Rust ecosystem, you probably know that under the hood, async functions are implemented as futures. But if you're new, there's no reason you should know that. So when I'm role playing here, I have no idea why we're talking about futures. But anyway, let's read it and find out. The futures crate contains traits and functions useful for writing async code. Well, actually, that sounds like what we want. Okay, let's keep going. This includes the stream sync, async read, and async write traits. Well, we had before the read trait, and we wanted an async version of it, so maybe async read is good. Okay, let's keep going. Futures has its own executor, but not its own reactor. Still don't really know what this means. So it does not support execution of async IO or timer futures. That doesn't sound great. For this reason, it's not considered a full runtime. Okay, well, let's keep reading. Popular async runtimes. There is no asynchronous runtime in the standard library. And none are officially recommended. The following crates provide popular runtimes. And then we've got a few crates here, one of which is a popular async ecosystem with HTTP, gRPC, and tracing. I actually want to read a file, but maybe that'll work. Who knows? The next one's a crate that provides asynchronous counterparts to standard library components. Well, that sounded like half the problem I had, but didn't it just say that futures would do that, but it wouldn't run my code? The next runtime is a small, simplified async runtime. Well, I'm not sure whether I want a small and simplified one or a popular one. do I actually want an async trait? I definitely don't want a Unix stream. And the final one is an executor for use in the future OS. And I don't even know what that is. So this is a really sucky situation. At this point, if I were kind of learning, I would want to stop. And I don't want you to think that I'm just kind of picking on the documentation here. The problem is the ecosystem, right? The documentation is an accurate reflection of reality, unfortunately. So at this point, I wouldn't really blame you if you just give up and decide to learn Go, because if you wanted to do this in Go, you just add the Go keyword and it's all async now. So that's kind of what we're up against and where we're at. If I've not convinced you to go and learn Go instead, if you're still with me, then I'm going to try and kind of like talk about how we might try and fix this in Rust. But first of all, like you might be thinking, well, like this sounds horrible. Why do we have multiple runtimes anyway? And this isn't just a mistake, or I don't think it's a mistake at all, to be clear. Um, in Rust, you're using Rust because you want precise control of the hardware. You're using Rust because you want to get like absolutely optimal performance out of your code. And we can write async code in lots of places. So if you're writing asynchronous code that is executing on like a tiny embedded processor, that's a really different context from writing asynchronous code that's executing on like a beefy rack server in a data center, like powering some like big cloud system. Likewise, if you're implementing like the file system layer of a database, that's a very different kind of context from implementing like a network load balancer. And so these different contexts have wildly different constraints. And that means that you might want different runtimes. And to really optimize like your code, which is why you're using Rust in the first place, right? Then uh, you might need not just like tweaks to the parameters of these runtimes, but actually like completely different architectures of these runtimes. It's not uncommon for people to write their own runtimes just to get the kind of like performance and other kind of characteristics that they need for their code. Kind of the problem with runtimes is that out of necessity, because there's been no support in the standard library for async programming, they've kind of grown beyond just kind of scheduling, executing your async functions. They've had to have their own like traits for IO, their own implementations of IO, utilities like timers, timeouts, concurrency primitives like channels, mutexes, fences, barriers, whatever. All kinds of utilities from like low-level things like pinning to higher-level things like combining features and so on. And the problem with this is that when you go to choose a runtime, you actually have to commit to like a whole ecosystem. And you can't operate with code outside that ecosystem that's using a different runtime. And that's a really like sucky position for the Rust community, for the Rust ecosystem to be in. And that's where the Portability and Interoperability initiative comes in. So my kind of like one sentence goal for portability and interoperability is that we want to support many runtimes. There's like really strong motivation for having different runtimes, but we want just one async ecosystem, right? We want you to be like, just because you choose such and such a runtime or you decide to write your own runtime, you are still able to use all these libraries that are out there in the async ecosystem. You're not limited to just those that have made that same choice that you have. The corollary to this is that it should be easier to switch runtime. If you start off using a general purpose one, but it turns out after a few months of coding on your project that you need something a little bit more specialized, then you should be able to make that switch relatively easily. And finally, like as I kind of like hinted in the motivation, well, probably more than hinted, we want to make it easy to start asynchronous programming. We want to remove a whole bunch of that friction that comes from having like multiple runtimes in the async ecosystem. To get a bit more concrete, the things that we want to do as part of the Portability and Interoperability initiative is we want to move a whole bunch of stuff into the standard library. So things like traits for I/O, utility functionality that can be shared across runtimes, that kind of thing. So there's kind of like standard issue stuff. We'd like some kind of abstraction over this concept of an executor to make it easier to change executors, although there's a lot of work to be done there. I don't know exactly what that abstraction will look like. Maybe we'll want to have some executor in the standard library. And we definitely don't want to have any kind of, you know, best executor or default executor or try and replace any kind of existing runtime. What we want to provide is the kind of minimum necessary executor for somebody to be able to start async programming, so they can learn how to do it, so they can kind of like start a project before they have to kind of have all this like deep knowledge that about their project or whatever to choose the best runtime. And there's also kind of like a bunch of kind of paper cuts that we want to get rid of in order to kind of just make async programming easier. So, like, what does the shiny future of async programming in Rust look like if we manage to achieve our goals? So let's go back to the example that I started with and see what it would look like. Well, it actually looks pretty much like what we thought it ought to look like. And that's kind of the good thing. But what's interesting is how that's possible. So first of all, let's look at the open function. Well, it would be nice if the standard library on file had not just the synchronous open, but an asynchronous open. And they might even be the same name, and we know which one to call based on the context. So here we're calling await. It's got to be the async function. Now, read to string, that's a function that's part of a trait. And so we should have like an async equivalent of the read trait that's in the standard library. And we can import that pretty easily, just like is shown on the first line of this example. Finally, to call this function, we should just be able to stick async in front of fun main in the same way that we can put result as the return type for main. And the compiler will just figure everything else out for us and it'll just work. Okay, so that's kind of what we want a simple case of async programming to look like in our shiny future. Okay, so for the remainder of this talk, I want to kind of like change the pace a little bit and dive kind of deep into the work I've been doing most recently as part of this initiative, and I want to talk about the Async IO traits and what they might look like. So the IO traits are in the standard library at the moment. Read, write, there's buff, read, and seek. And we want kind of like asynchronous versions of these. And I'm just going to talk about read to kind of try and illustrate some of the issues with async traits and what the eventual design might look like. Some of the same things apply for kind of for write and seek and so forth. But limited amount of time. So this is a vast simplification of the current read trait in the standard library, the current synchronous version. So there's just a function read. The trait abstracts over kind of a resource that can be read, and so there's a function read. You pass it a mutable slice of bytes, and it will read into that slice, and it will return you the number of bytes returned. So async read trait, maybe it'll look like this. The only thing that's changed is we've got the async keyword in front of the read method. And now we can await this, and we can kind of get on with something else whilst the operating system or whatever is doing the read. And you can't do this right now. We need async methods in traits, but like I said earlier, this is something that the async working group is looking at and hopefully will be implemented soon. And so then this will just work. And I think this is a really great starting point. It matches very closely the synchronous trait, and so it should be very easy to transfer your knowledge and experience from synchronous programming to asynchronous programming. But it's also only a starting point. And to kind of like explain why, I have to kind of get a bit more into the details of how asynchronous IO can work. So I just want to start going back with sync. So here's how a read call works in kind of the synchronous universe. So the user process, probably via a library, initiates a read to the operating system. The operating system actually reads from the resource. This could take some time. And when that read is done, the operating system returns that read data back to the user process, and the library presumably will pass it to the actual user code. And like I said before, the downside of this is that while the operating system is doing all this reading, the user process is just sat there twiddling its thumbs with nothing better to do. So the async equivalent of this, there's actually like a couple of ways that async IO can work. Well, more than a couple. There's a couple that we're really interested in. There's the readiness model, and this is what epoll on Linux uses. And there's the completion model, and this is used by IOCP on Windows and IOUring on Linux. So I'm going to go over how both of these two models of async IO work and how that kind of affects the design of an async read trait in Rust. So let's start with readiness. So again, the user process initiates the read, but this time the operating system immediately returns. And that gives the user the user process some opportunity to get on with something else, right? So that's getting us the async benefit that we wanted. Meanwhile, the operating system is doing the read from its resource in exactly the same way as before. And when that read is done, once the operating system has read that data into its internal buffers, it's going to tell the user process somehow that it's ready, that we're done. And at that point, the user process can read the data out from the operating system extremely quickly. Right? So this is the async call. The nice thing about this is that the user process doesn't need to provide a buffer for it to read the data into until that data is ready to read. So that means if it's allocating, can allocate that buffer like at the last minute, just in time, and then pass the buffer to the operating system and to fill up. It doesn't need to pass the buffer when it's initiating the read. And this can be really important. So consider if this is like a web server or something similar. Then when the operating system is reading from the resource, it's not necessarily just reading the bytes off a disk. It could be waiting for those bytes to arrive from a remote host. And if that remote host is waiting for a user somewhere to like type into a web browser or something, you could be waiting a really long time for this IO to complete. And of course, it's a web server. You're not dealing with just one client. You're potentially dealing with many, many clients, each of which is waiting on one of these reads. And because you don't know how many bytes you're going to get back, this buffer has to be quite big. So you've got many, many quite large buffers that have to be held for potentially quite a long time. And that would be a huge waste of memory. So being able to kind of like have this memory kind of like on a kind of just-in-time basis is a really big advantage for the readiness model. Completion is the completion model for async IO is a bit different. Again, we initialize the IO with a read. The operating system returns immediately. The user process can get on with some work whilst the operating system actually does the read. But this time, the operating system tells the user process not when it's ready to read, but then when the read is completed. And the way this works is the user passes a buffer to the operating system, or a reference to a buffer to the operating system when it initiates the IO, and the operating system hangs on to that, writes directly into that, and then notifies the user when the buffer is full. Okay. Now, you obviously lose out on the advantage of readiness that I was just talking about having this just-in-time allocation of buffers. But what you get instead is that the operating system can read bytes directly from the resource into the user's buffer, and so this can end to end. You only have like one read into a buffer, so it's a zero copy process, and that can be really efficient. So if you're doing disk I/O, for example, then completion has a whole bunch of advantages in terms of efficiency over readiness. All right, so that's a lightning quick explanation of how async IO works. Let's see how that relates to the async read trait. Well, um, before I said we could just have like an async read method, but unfortunately that doesn't really work very well for either model. For readiness, um, the because we only have this one function, we have to start that right at the beginning. There's no opportunity to pass the buffer in later, so then do this just-in-time allocation of the buffer. We have to pass it in at the beginning, and so we lose this like big advantage of readiness. To get around this, I'm proposing we have another trait. So as well as just having the asynchronous read trait, we have a trait that is called ready. So now you have two options. If you don't care about this memory usage so much, then you can just use the asynchronous read method. Very ergonomic, does what you'd want, very easy to use. Great. If you need to be writing memory optimal code, then instead you can call the asynchronous ready method. And note that we don't pass a buffer in here, okay? I've elided a few things from the example, but it's just flags, basically. And so so your task would wait for the ready method to complete asynchronously, and when it returns, it says, "Hey, I'm ready," and then you can call this non-blocking read function. And notice that this isn't an asynchronous function. This is going to return immediately, and in fact, it promises not even to block like the synchronous read function does. And that's when you pass the buffer in, and so you have this opportunity to do the just-in-time allocation or to reuse buffers or whatever, because you have this opportunity to get that memory between when ready completes and when you call the non-blocking read function. So let's look again at completion. So in this case, you do pass the buffer in the beginning, but unfortunately, this still doesn't work with the simple async read method, and that's because of cancellation. So if we were to do the simple async read with the runtime were to pass this buffer straight to the operating system, then one aspect of async programming in Rust is that you can always cancel a feature like an async function. And if that were to happen, then the buffer might get deallocated, right? Because as far as the Rust world is concerned, you don't need this buffer anymore. The future was cancelled. But unfortunately, just because the future was cancelled doesn't necessarily mean the read with the operating system was cancelled. The operating system could have already started reading. And if that buffer has been deallocated and the operating system is reading data into essentially just a dangling pointer. And kind of the whole point of Rust is that we don't read data into a dangling pointer. So this is very suboptimal. And So the problem here is really one of ownership. So we're passing like a slice of data from the caller of the read function all the way into the operating system. But logically, we actually need to transfer ownership to the operating system because the operating system has to own the buffer. It has to be the one that's the only one who's able to write into that buffer while it's doing the read. So this actually fits kind of well with the buff read trait. So I said earlier there's the read trait and there's also the buff read trait. And the buff read trait is a version of reading where we read into a buffer that is managed internally rather than having a buffer that the caller manages. So if you're happy for the runtime to manage your buffers, then using buff read is a really nice fit. Rather than calling like the read from the read trait, you call read on buff read. The runtime takes care of the buffers. If it's cancelled, the buffer isn't deallocated, so you never have this dangling pointer situation. And you just get back a slice of data. So this is great. This fits the completion model really well, and it means that the operating system can still be zero copy. The problem is that we're returning a borrowed slice of data to the caller. And that's okay if the caller is going to immediately consume those bytes. But if the caller wants to store those bytes, then the caller has to copy the bytes. Whereas what we'd like to be able to do is the caller to pass in a reference to the buffer that it owns, which the operating system can write directly in. So it's zero copy both on the user process side and in the operating system. So a possible solution to do that is yet another trait. And owned read is a terrible name for this trait. I haven't figured out a good one yet. But the idea is that it's very much like the read trait, except rather than passing in a borrowed slice, we pass in an owned an abstraction over an owned buffer. So owned read buff is just a trait that you would implement for like a vec of U8 or for your own kind of custom data types, so that you could temporarily transfer ownership into the library and kind of hypothetically the operating system, so that the ownership works out. And this kind of model seems to work really well with the completion system. It's kind of the part of the design that's still the most up in the air, but I'm hopeful that something like this will work well as part of as kind of suite of async IO traits. Okay, so that's kind of all I've got for this talk. Just to quickly summarize, I kind of gave you some motivation on what async programming is like today and why we need to improve that. I shared kind of the goals of the Portability and Interoperability initiative, primarily that we support many runtimes within a single async ecosystem, making it easier to switch runtimes and making it easier to start asynchronous programming. And I also got a little bit into the design work that is kind of currently ongoing with the Async IO traits. So that's all I have today. Thanks for attending this talk and for paying attention. If you're interested in this work, the Async working group does all its work in the open, mostly on Zulip. So log on to Zulip, the Rust Zulip, and there's a stream for the Async working group, and you can see all the discussions we have there. And I'm Nick Cameron on Zulip. If you want to follow this work on social media or whatever, I'm Nick R. Cameron on Twitter and NRC on GitHub, or if you prefer email, that's on the slide. And thank you again.